Look, at the end of last time, and in our quest to turn everything into a polynomial if possible, I want to revisit the example we left off with last time. Okay, hang on a second. I have to get this thing to work correctly. Here we go. Okay. Let's make sure this thing is working. It's not working yet. Let's see. Come on, Apple Pencil. Here we go. Yep. I want you to work. Yes. Thank you very much. Okay. So what I wanted to do was revisit this example that we were looking at last time. Namely, I want to find the Maclaurin polynomial or polynomials, which means polynomial of any size for the following function, f of x equal to logarithm of 1 plus x. Now, the reason I asked you last time, why is it that that I would look at logarithm of 1 plus x as opposed to logarithm of x? Well, the Maclaurin polynomial has powers of x in it, right? And the center is 0. So what are we plugging into the various derivatives in that case? 0. Can I plug 0 into the logarithm function? No. And I can't plug 0 into any of the derivatives either. Yeah? So that's kind of what's going on here. And what we did is we realized, all right, no, we're going to take some derivatives. So here's like the first derivative. Of course, that's 1 over 1 plus x, which, by the way, is the same thing as 1 plus x to the negative 1. Yes? We discovered that the second derivative, okay, if you think about it as 1 plus x to the minus 1, that is going to be negative 1 times 1 plus x to the what? Negative 2, yeah? Third derivative at x, the negative 2 comes down, and it's going to be 2 times 1, right? Because the negative sign cancels. 2 times 1 plus x to the negative 3. Do you see what's happening with each subsequent derivative? It's spitting out like the next number in what looks like a factorial of some kind. And the other thing that's happening is it's kind of flipping signs back and forth, yes? Kind of flipping signs back and forth. Okay, the fourth derivative at x is what? Negative. Okay, let's stop horsing around here. It's negative 3 times 2 times 1. What do we call that? Negative 3 factorial times 1 plus x to the negative 4. This, of course, is 2 factorial. 2 factorial times 1 plus x to the negative 3. Of course, this guy I could have thought of as negative 1 factorial, 1 plus x to the negative 2. And I mean, this guy, even this guy, I could think of it as sort of stupid, but I can think of it as 0 factorial if I really wanted to, right? 0 factorial times 1 plus x to the minus 1, if you will, right? What is the deal? What is the formula for the nth derivative here? The nth derivative at x is, it looks like, it basically n minus 1 factorial, okay? N minus 1 factorial times 1 plus x to the negative n. And how do I decide whether the sign is positive or negative? How do I decide whether the sign is positive or negative? Well, like if it's an odd factorial, it's negative. If it's an even factorial, it's positive. Does that make sense? If you stare at that for a minute. If it's an odd factorial, it's negative. If it's an even factorial, it's positive. So like I could just raise minus 1 to whatever factorial we happen to be on, and it's going to do the job for us. Does that make sense? So it's actually minus 1 to the n minus 1, yeah? And then, of course, if I were to write this thing as like C0 plus C1x plus C2x squared plus dot, 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 plus Cn x to the n plus dot, 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 right? So those are basically the terms of my Maclaurin polynomial. We know that the formula for Cn is the nth derivative of f evaluated where? If I'm just having powers of x, center is 0. Where do I evaluate the nth derivative? At 0. And I divide by in factorial, right? So in this case, what do we have? Think about it. What is the nth derivative at 0? If I plug in 0, of course, it's going to be 1 plus 0 to the negative n. That's just 1. And I just end up with negative 1 to the n minus 1 times n minus 1 factorial. Okay? Interesting. Okay, so I plug that in up here. So it's like negative 1 to the n minus 1 times n minus 1 factorial. Downstairs, what's n factorial? What would be kind of a better way to write that so that I can see cancellation happen here? In factorial, how should I write that so I can see clear cancellation happen? Yeah, I just write it as n times n minus 1 factorial, and then clearly I have some nice cancellation, and I just end up with minus 1 to the n minus 1 all over n. Of course, for this little formula to make sense, I need to be at least at the first derivative. The first derivative is where the pattern started to emerge. So let me just say n greater than or equal to 1 here. By the way, what is C0? Think about it. Remember, C0, wasn't that just f of 0? That's how we would have gotten that, yeah? And what happens if I plug 0 into the logarithm function? What do I get? Logarithm of 1, which is 0, yeah? So C0 is that. Okay, and the rest of the terms, you know, like, so this term right here is going to be minus 1 to the n minus 1 over n times x to the n, yes? So in general, you have kind of this alternation in signs, and you basically have something that kind of looks like the alternating harmonic series. Do you know what I'm saying? It looks like the alternating harmonic series, if you think about it for a second, but it just has an x to the n attached to it. Okay? Any questions on that before we go look at this thing visually? Questions? We kind of came up with that at the end of last time, I know, but I just want to make sure we write down the formula and kind of look at this thing visually. So any questions at all? Okay, well, here we go. Let's kind of plug this thing into, let's see, I'm having a hard time seeing here. Where is my Desmos? I think it's here somewhere. Here it is, right here. Okay. So here I already kind of plugged this thing in right here. Okay. So you see here's the function logarithm of 1 plus x. Do you see that? Yeah. Ooh, man, let me pause this thing. I don't want this thing to go hog wild on us here. Okay, let me click out here so that it gets rid of some stuff. Let me go back to the beginning here. Okay, I'm sure, like 0 is stupid. You understand? What did we figure out that the constant term was? Wasn't it just 0, right? Yeah? The constant term was 0, so I mean, that's going to be equal to logarithm of 1 plus x at 0, but it's not going to be very helpful. In fact, I'm inclined to kind of tweak this thing a little bit. Let's see, I'm going to start at 1, okay? So n equal 1 to 50 with step sizes of 1. Okay, done here. Okay, so the first approximation would just be the tangent line at 0, yes? And what's the second? Here's the parabola. It's a slightly better approximation. Do you see that? Okay. There's the third. Fourth. Getting better. Fifth. Look, you see the lizard tail here. Sixth. Seventh. Eighth. Ninth. 10th. 11th. 12th. 13th. 14th. You see that? thing is getting closer and closer and closer over there on the left, but you see have this lizard tail kind of whipping up and down on the right, yes? Okay. Oh, okay, so look at that. Okay, in fact, let's kind of push this thing to the 36th thing. That's almost becoming indistinguishable on the left, but what do you notice is happening over on the right, unfortunately? It's getting closer, but it starts to get bad around where? Or where does it start to get bad? 1. Starts to get bad around 1, yeah? In fact, that doesn't seem to be getting any better no matter how high up I go. So there's the 45th degree polynomial. Do you see? It's still bad at 1 or just beyond 1 every single time, yeah? And why I'm showing you this is I want you to be aware that really what's controlling that is the fact that how far back, like how far away from 0 can I go to the left and still have this function make sense? How far down to the left can I plug in a number into that logarithm function and still have this make sense? What's that? Something slightly greater than -1. So 1 away to the left, yes? And it turns out there's a nice symmetry with these things. If that's as far I can go on one side, then it turns out a similar thing is going to happen going in the other direction. You're going to have the things start to not work if I go any further than just 1 to the right of 0, the center of my approximation, yeah? The center in this case was 0. Okay, it really doesn't matter how high I go on this. You know, even 49, 50. Look, it just keeps getting better and better and better between -1 and 1. But then the minute I get to the right of 1, things just go wildly wrong, yeah? And I'm not staying close to the function anymore. That's something we're going to be looking at more deeply later on, okay? All right, so any questions on that? I think that's kind of a cool little visualization of what's happening. Any questions on that? Okay, so going back here, let's go in here. I wanted to use this to approximate something. So use the 4th Maclaurin polynomial to approximate the logarithm of 0.9. Okay, now what did we just find out? So let's kind of write this in here just so that we have it. We found out that logarithm of 1 plus x, what is the 4th degree polynomial? So let's write, so P4 of x. So what is P4 of x? What was the constant term again for this thing? The constant term was 0. And then there was depending on what power I was on, I had a negative sign, yes? So if n was odd, the sign was positive. That was kind of weird, right? Because we went -1 to the n minus 1, correct? So like if n is 1, we would have gone -1 to the 0, which is positive, correct? Okay? So I'm telling you, the 4th polynomial would have been x, and then minus, what would the next thing have been? That next thing would have been minus something times x squared. Right? Minus what times x squared? It was 1 over n, x to the n, right? So it's minus 1 over 2x squared plus 1 over 3x cubed minus 1 over 4x to the 4th. And here I've asked you to approximate the logarithm of 0.9 using the 4th degree Maclaurin polynomial. Okay, so what would you plug in for this? So actually, I don't say it out loud. What I want you to do is talk to someone around you and figure out what you would plug in and actually do it, like into your calculator or something, and tell me what you get as the approximation for this using the 4th degree polynomial. So, you know, this is, you're basically going to take the 4th degree polynomial and plug something in here, okay? So think about that with the with your comrades nearby and tell me what you come up with, okay? All right, I already heard someone mention something. So basically, this is So 1 plus x, okay. 1 plus x, you want that to be equal to what? You want 1 plus x to be 0.9, which means you should plug in x. So x should be what? Negative 0.1, like to make this thing work out. 1 plus that thing needs to be 0.9, yes? Okay? So this thing is going to be apparently pretty well approximated by P4 of negative 0.1, okay? So you need to plug negative 0.1 into this. What do you get when you get that? Anybody do that? Negative what? I don't know, 4? 0.1054. And what is the true value? What is the true value of this thing? You guys compute that. What is, I mean, I know that in your calculator, you probably have logarithms in there. So it's basically the same thing. Logarithm of 0.9 is what? Negative 0.10536. Wow, that's pretty impressive, right? I mean, we've only taken the 4th degree polynomial, and this seems to be giving a pretty decent approximation. Of course, negative point, well, the key is that, that negative 0.1 isn't that far away from 0. Does that make sense? The best approximations are going to be at 0. We haven't deviated too far away from 0 yet. Okay? So that is the key. Okay, any questions on that? I think that's kind of cool. And by the way, this is what computers do. Do you ever wonder how computers compute things like logarithms? Like, is there just a table somewhere? And even if there was a table, just think philosophically about it. You would have this like infinite regression. Okay, if there's a table, where did that table come from? Hello, right? I mean, eventually you would have to realize there's got to be something driving this forward. And what it is power series, okay? Sort of these basic polynomial approximations of things, or what actually gives the values of these functions, okay? All right, cool. Moving on. So just some basic facts about accuracy. A Taylor polynomial more accurately approximates the function the larger the degree is, duh, right? So the more terms I take, the better the approximation is going to be. But also the closer x is to the center, yeah? Remember, the center of approximation is perfect, and it starts to fall away the further I deviate from the center, yeah? So higher degree, closer to the center, you're going to have better approximations, okay? And you might say to yourself, okay, well, how accurate, right? How accurately does this thing approximate? Well, let's talk about that a little bit, okay? So suppose, I have my function, I have the approximate value, so here's the, the polynomial approximation right here, okay? And then I have some remainder, like error term, that tells me how far off I am. Does that make sense? And basically what I'm going to do is I'm going to take the error and write it as the difference between the function and the polynomial value, okay? So that's the error right there, okay? So the question is, how far, you want this to be, right, in order for the approximation to be good, you want that Rn of x to be, right? I want this to be small. Okay, so want to be small. Okay? All right, so that would kind of be the goal of this thing. Okay? So here's like here's Taylor's theorem, okay? And basically what it says is, okay, what is sitting right here? This guy right here is Pn of x, right? It's the nth Taylor polynomial. Okay, that's the formula for that thing. And then I have the remainder term, which is basically the error. And what this says is the largeness of the error has to do with the n plus first derivative of the function, okay? That's really all I want you to know. The largeness of the error has to do with the next derivative of the function. That's what controls how big the error actually is. Okay, and that ought to remind you of something from our past already. You remember a situation where the difference between a partial sum and the whole sum had to do with the next term? What was that? Alternating series, yeah? And it's the same sort of thing here. The largeness of the error is controlled by the next derivative, basically. Okay, that's what's going on here. I'm not going to go into the details of that, but it turns out if you were ever like really concerned about your Taylor polynomial not being a good approximation, you could think about the next derivative and actually figure out, well, I can't be off by more than this, yeah? I can't be off by more than like to the thousandths position or something because the n plus first derivative is this small, okay? At this particular value, okay? Any questions on that? So the remainder is controlled by the next derivative, the very next derivative. That's all I want you to get out of that. Questions? I'm not going to go into this. Look, but let's actually compute this. Find an upper bound for the error. Who cares about that? I actually want to. This right here is right. So this is P4. Looks like I've taken P4 for the cosine function. We found the cosine function before. I've taken P4 and what have I plugged into it? 0.2. Can you guys compute that? And then let's compare that to what the cosine of 0.2 actually is. So make sure you're in radian mode, okay, not degree mode. But can someone compute what the cosine is and what this thing is? Just so that we can compare the two. Cosine of 0.2 versus the fourth Maclaurin polynomial evaluated at 0.2. What do we get?
It's the same as
0.9801 for cosine of 0.2, and you're telling me it's like basically the same thing here?
Yeah.
Yeah, so the error is quite smallish, yeah? It's amazing how some of these, especially if you have factorials in the denominator, it's amazing how quickly the error starts to subside. If you have factorials in the denominator, you end up getting polynomial approximations that are very good, very fast, okay? So for instance, let's do another example here. Let's see. Let's go to the whiteboard. So watch this. You guys remember we did e to the x last time, and what did we find out was the kind of the series representation of this? Do you remember it was like x to the n over n factorial? Do you remember that? So this thing is like 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, right? Okay. What would be a good approximation for e? Think about it. By the way, then this thing just keeps on going forever. But what if I just decided to truncate this thing right here? Okay. I just took P4 of x. What would be a good approximation for e? Like e, by the way, that's just e to the first. Do you know what I'm saying? Yeah? So wouldn't that be apparently pretty well approximated by the fourth Maclaurin polynomial, P4, evaluated where? Where would I have to evaluate this thing? 1. Right, so try that out. 1 plus 1 plus 1 over 2 factorial, which by the way is a half, plus a 6th, plus a 24th. You see that? What is that equal to? Can someone compute that? What's that equal to? 2.708? And we could very quickly get an even better approximation by going to the next term, which would have been 1 over 5 factorial, which is 1 over what? 1 over 120, right? So I could get a better one like P5 of 1. In fact, let's go a step further, all right? Let's not horse around here. Let's do 6 of 1. Okay, so this would be 1 plus 1 plus 1 over 2 factorial, which is a half, plus 1 over 3 factorial, which is a sixth, plus 1 over 4 factorial, which is a 24th, plus 1 over 5 factorial, which is 120th, plus 1 over 6 factorial, which was 1 over 720. You know what I'm saying? What do you get when you do that? 7181, basically. And that's starting to get closer to what you know as the number e. Does that make sense? So the more terms you take, the closer you're going to get to the actual decimal rendition of the number e. That's sort of interesting. Yeah, I had to take more terms there, but that's probably not that surprising because where is this thing centered? Where are the best approximations going to be? 0. And I've moved 1 away from 0 at this point, right? So I mean that's not like a violent move away from 0, but it is significant. So it's not surprising that I have to actually take more terms to get a better and better approximation. Yeah? That's kind of interesting. Questions on that? Any questions? Okay. Let's move on. Done with that. Okay, and let's go on to the next thing here, which is on power series. Power series. Now, we talked about polynomial approximations. The way that I taught this, though, you should have seen power series on the horizon anyways. Like, why stop? Just keep going, yeah? Just let the thing go crazy, yeah? So we've already seen some power series renditions of some of the basic functions we might be interested in. We did it for cosine. Basically, it wouldn't be too hard to come up with sine as well. We did it for e to the x. We did it for logarithm of 1 plus x, but we'll do some other ones as well. Now, one thing you may have noticed is that when we did logarithm of 1 plus x, things seemed to be going wrong eventually, yes? When we centered the thing at 0, when we went 1 away, it seemed like there was no hope beyond 1, yeah? Something was wildly wrong once we got to 1. And so that gives rise to the idea of a radius or interval of convergence of a power series. That sometimes you can't just plug in any number you want. You can only plug in things up to a certain point, yeah? And if you wanted to plug in other numbers, you would have to recenter the power series. You know what I'm saying? You have to kind of recenter things and start the approximation over again by recentering the thing. Endpoint convergence of a power series is a big deal, okay? Usually you have like an interval of values you can plug in, but there's a question as to whether you can plug in the left and right endpoints of the interval, okay? And differentiation and integration of power series is going to be a big question because that's one of the reasons we started this discussion in the first place, is what is the easiest function in the world to deal with calculus-wise? Polynomials. We want to turn everything into polynomials if we can. And we want to know if when we take derivatives and integrals, whether we still preserve the actual function itself. And the answer is yes, okay? We do. So in general, a power series looks like this. Okay, x is just a variable, and a power series looks like this. You just have an, and you tack on an x to the n. It still looks like a series, but you just tacked on an x to the n, yes? Let's say 0 plus a1x plus a2x squared, etc. Or I may decide I don't want to expand in terms of powers of x, but powers of like x minus c, where c is the center. Is this not sounding exactly the same as what we were doing with like Taylor and Maclaurin polynomials, yes? It's the same idea, except we're just not stopping. Like we just let this thing go on forever, okay? And so that's the definition of a power series. It's a series because it never stops, Okay? Otherwise, you would have just said it's a regular old polynomial or just a sum. Yeah, finite sum. How do you think how do you think these things would be determined? Okay, like the ANs that happen to be sitting right here. Well, we already did that, didn't we? We actually already found a formula for those things. It's right here. There's the formula right here. Yeah. Okay, so that formula just goes right there. Okay. That's what it is. It is the exact same computation that we did before. So to find, actually, hang on, something's wrong with that thing. What should I not have in that formula, to be honest with you? What should not be there? AN is the actual number that's sitting in front of x minus c to the n. So what shouldn't be there? That stuff should be gone, yeah? AN is simply equal to the nth derivative of the function evaluated at c divided by n factorial. It's the same exact process that we went through before to find that. That's what the formulas are going to be given by. Okay? Continually taking derivatives, plugging in c to figure out what those coefficients would have to be on x minus c to the n. All right, so again, this thing should not be here. That's a typographical error. Let me just color that over in red so you're not tempted to think that that's part of the formula. Yeah? Okay? But seriously, is this not the same thing that we were basically talking about last section? Yeah? Except there we were somewhat interested in kind of stopping the process at some degree. Here we're just letting it go on forever. Right? Okay. So what is the domain of that power series? Well, it's the set of all x values for which the series converges. And that really is the main question. What x values can I apparently plug into this thing? Like when we looked at the situation for a logarithm of 1 plus x, it looked like the series worked well until we started trying to plug stuff in that was beyond 1. And then it looked like stuff was just not right anymore. Yeah? Something was going wrong. So one of the big questions we're going to have is what x values am I allowed to plug into this thing? And the x values that I can plug in, that's going to be called my interval of convergence. Interval of convergence. Okay? So all power series converge at x equal to c, obviously. You know what I'm saying? Like if I plug in x equal to c, what happens to almost every term in the series? Okay, it goes away. And all you're left with is the constant term. Does that make sense? So every power series converges at the center. There's no question about that, yeah? Okay, the only other question is, okay, so like if I plug in x equal to c, for instance, I get f of c is equal to, so what am I going to end up with here? Look, everything dies beyond n equal to 1. So f of c ends up being a0, just the constant term, yeah? That's it. Okay? But then, this is just we're going to end with this, but I just wanted to point this out. But then sometimes I'll be able to plug in a lot more than that. It won't just be a single point, but sometimes you'll actually have an entire interval. Okay? And it turns out that, yeah, it will actually be a symmetric interval about the center, where I can go r to the right or r to the left. And that will be my interval of convergence. Okay? Or sometimes what will happen is every number is allowed to be plugged in. Didn't we see that that was kind of what was happening with sine and cosine and what else? Eventually, if I took enough terms, it looked like I could plug anything in, right? Sine, cosine, what was the other function we looked at? The exponential. It looked like those guys, I could actually plug anything at all in. But with the logarithm function, there was kind of a smaller collection of values I could plug in. It was an interval of values. Okay? So I just wanted to point out those basic facts, and that will kind of set us up for what we will do tomorrow. Okay? Any questions? Yeah, Daniel.
So, will for the interval, so if we have a radius like with the logarithmic function, it's not continuous for all of them. So like, in other words, it has an asymptote at some point, right?
Yeah, right. So the logarithm function had an asymptote, and in some sense, that's controlling what the interval is. Yeah.
So like, if there's an asymptote,
Yeah, sometimes, but sometimes that won't be the case. There are cases where you have like an interval of values that you can plug in, and the function is still defined elsewhere, but the power series only works in like a narrow window. Okay. All right. To be continued.